Okay, this video is our final video in Unit 3. Today we're going to be dealing with essentially two topics: interpreting the domain and range, and then interpreting the rate of change in models of linear functions. So first let's deal with the rate of change. This is from a previous problem we dealt with. We have an airplane. It's ascending and taking off at 1,800 feet per minute, or climbing, I should say, at 1,800 feet per minute until it reaches a maximum height of 41,400 feet. So interpret the rate of change in terms of the context of the problem. That's my first question. Now, the rate of change, if you remember, and it's indicated over here, is the number 1,800. It's the slope in the function. So this is a linear function. It's in slope-intercept form. It has a slope. It has a y-intercept. So 1,800 is the number we're dealing with, and we're trying to interpret that 1,800. What does it mean? So the rate of change, that's the slope. And if you remember, the slope, or m, is just simply the change in y over change in x. So if we take this number, 1,800, and we rewrite it as a ratio, right, including units. So first is a ratio that just looks like this, 1,800 over 1. So if the number is an integer, you can always put it over 1. Now, written as a ratio, this means you're comparing two values that are increasing at the same time. This is 1,800 feet over 1 minute. So you want to provide that context of the situation. How do I know it was feet and minute? Well, the change in y. Y is my dependent variable. That's the plane's height. So how is the plane changing? Well, it's increasing, and I'm going to indicate that by a plus sign here, by 1,800 feet. And then how is my change in x, my time increasing? That's increasing by a minute. So you want to basically write a sentence about this, and I'm going to give you two ways to write a sentence. The first is this. You can basically use this shell, which is on the bottom of the slide here. This we've seen above, basically 1,800 feet over 1 minute, written as a ratio. So if you consider this shell, meaning like you can take any contextual situation, and that is represented by a function, and say as the independent variable increases or decreases by whatever delta x is, including units, the dependent variable increases or decreases by whatever delta y is, including the units. So in the context of this problem, that is as the time increases, because that 1,800 is a positive number, by 1 minute, then the plane's height increases by 1,800 feet. So you can always use this shell and just plug in what was representative of the independent variable, and then the delta x, including the units, what's representative of the plane's height, and then delta y in this sentence. So written as a sentence, this looks like this. As the time increases by 1 minute, the plane's height increases by 1,800 feet. This is a well-developed sentence that describes the rate of change contextually, using English words and phrases. Okay, here's another method you can use. The same ratio, 1,800 feet over 1 minute, written using the units. If you phrase 1,800 feet over 1 minute, and the fraction bar that's in between these two values in the ratio using the word per, and then just add a noun and add a verb, meaning this here. The plane, my noun, ascends, my verb, 1,800 feet per 1 minute. So you just take the phrase, you read this ratio, 1,800 feet over 1 minute, but instead of saying over, you're saying the word per for the fraction bar, and that then represents that sentence. So 1,800 feet, or a part of that sentence, 1,800 feet per 1 minute. Okay, well, add a noun, add a verb. What is 1,800 feet per 1 minute? What's happening? What's the person, place, or thing that this 1,800 feet per 1 minute is happening to? The plane. What's the action word? Ascends. The plane ascends 1,800 feet per 1 minute, and you're done. This, I think, might represent maybe generally an easier way to write down the rate of change contextually. Okay, so that's interpreting the rate of change. Second thing we're doing is interpreting the domain and range in the context of the problem, or determining a reasonable domain and range, it's called. So same situation. The 747 airliner is climbing 1,800 feet per minute. It's I'm reaching a maximum height of 41,400. Basically, the domain is all the possible values of the independent variable. The range, all the possible values of the dependent variable. This domain is basically a minimum and maximum in the independent variable of the time. What's the minimum time according to this function? What is the maximum time? Now, same thing for the dependent variable. According to this function and the context of the function, there is a minimum of the plane's height. There is a maximum. Okay, so you're going to have to sort of logically deduce at least 3, most likely, of these values, meaning minimum and maximum for both the domain and range. And it turns out that some of this information is given in the problem, and some of it you're going to have to logically deduce. So let's go with the easiest thing first. It says in the context here, a height of 41,400 feet, a maximum. Well, this in here, that's my maximum. Right? 41,400 feet. So is that the plane's height or the time? It's the plane's height. So I know my maximum of the range is 41,400. Okay, what else can we deduce? Maybe the minimum. You always want to think about is, do negative values pertain in this situation? Meaning, like, is there going to be such thing as a negative plane height? Well, no. This plane is taking off from the ground, and it's ascending, starting from height 0 and then continuing up. It never goes down. It never goes down past 0 because that would be the plane flying into the ground. That's not going to work. That's not a reality. So for that reason, we can say that the minimum value of the range is 0. Okay. Contextually, what about the domain? Time minimum, time maximum? Is there anything that we know? Well, we can say, and we always want to think about it when you think about a real life situation, like I said, do negative values pertain? Meaning, like, is 0 a boundary of the function? Is it a minimum? Is it a maximum for some reason? Most times it's a minimum. But could 0 be a minimum here for time? Well, yes. What does negative time really represent in this case? Negative time means the time before the experiment. You're not worried about that time. And by experiment, I mean the situation in which this, these independent and dependent variables are interacting is taking place. So in this context, this is a plane which is taking off. It's climbing at 1,800 feet per minute. Now, do we worry about the time before it takes off? No, there's no context there. It's not climbing 1,800 feet per minute at all during that time. We've defined this function to be only from the point when it takes off to the point when it reaches its maximum height. So for that reason, the minimum value is 0. Negative values of time are just like, let's say that this was, not let's say, this is 1,800 feet per minute, so the units is in minutes. A value of -3 in the domain would mean 3 minutes before the plane took off. Well, it's not climbing then. It's not climbing at 1,800 feet per minute. The function hasn't started, so it's not relevant. So therefore, the minimum value of time, and this is the case for a lot of functions, is 0. Because we don't worry about the time from before the experiment. Okay, so we have these 3 values. We have minimum of 0, a minimum of 0 for the independent and dependent variable of the domain and range, a maximum of 41,400. Well, what does this really represent? Let's look at this table in the bottom here. This minimum is a coordinate point, 0, 0, meaning at time 0, the plane's height was 0. There's also a maximum, right? That means that at some time, the height was 41,400. So in order to figure out these boundaries of the domain and range, all you need to do is figure out what's this x value here that's associated with 41,400. Well, it turns out that value is 23. And I can get that or obtain that value of 23 by solving the function in the same way that we did in previous problems. So I have my function, f of t is equal to 1,800t. I'm plugging in for 41,400 for f of t, a height. I'm trying to figure out the time t that's associated with 41,400. So I divide both sides by 1,800. I get time is equal to 23, and that's how I got my 23. So I actually have to solve an equation, right? And solve the function in order to attain this maximum height. So now I have both. I have my minimum at 0, 0. At time 0, the plane's height was 0. And I have my maximum After 23 minutes, the plane's height was at a maximum of 41,400 because above 41,400, passengers start passing out and it's not safe to fly above that altitude. Okay, so this is essentially the domain and range. It's the minimum and maximum of all the possible values of the function based upon your deductive reasoning. How did you reason it? Okay, how do you write that mathematically? This is how the domain is written, using something called a triple inequality. Using less than statements in between, like a less than and a less than in between the numerical values, the three of them in the triple inequality. The minimum and maximum of the domain are on either end, minimum on the left, maximum on the right, the variable which is representative in the middle. Now notice that I'm using less than or equal to statements. That's because it's okay for me to have at time 0. It's okay for me to have time 23. If for some reason it said after 23 minutes, the plane couldn't climb anymore, then you wouldn't use 23 and you would use less than instead of less than or equal to. So these inequalities matter in the context of the situation. So basically, what is that? That means this number line. It means that the domain can take on all the values between 0 and 23 inclusive. So like the time starts at time 0, time elapses, goes on and on, plane's climbing, and up to minute 23, that's when it reaches its maximum height. Range, same notation, except using f of t instead of t, the minimum and maximum on either side as before. You're also using less than or equal to because the values of 0 and 41,400, it's okay for the function to take on these values. It said maximum height of 41,400. It didn't say it couldn't be 41,400, but it could be any other values that are below it. No, it said 41,400 was okay, so I'm using less than or equal to because it's okay for it to be equal to. So these triple inequalities is a way to mathematically represent the domain and range. Once again, this range is really, you can represent it using a number line. It means that the plane's height starts at 0 and climbs all the way up to 41,400. So all these values pertain, all the values that are shaded inside of the number line pertain in the actual function. And this is just a way to represent this domain and range. On the portfolio test, you can also talk about this in a sentence, but you'd have to use the words less than or equal to, or greater than or equal to, depending on what the situation calls for. Like I could say, the time is greater than or equal to 0, but less than or equal to 23. And the plane's height is greater than or equal to 0, but less than or equal to 41,400. So you could say that if you wanted to. But these down here, this domain and this range, which I'm going to highlight in blue, right? This here, that's my final answer highlighted in blue. The two inequalities, or triple inequalities, which represent that minimum and maximum value. Okay, this concludes Unit 3.